Hello viewers, welcome back to our discussion on vibrational spectroscopy. In today's session, we will talk about vibration frequencies and their significance. The session is planned as follows, that is, to begin with, we will review what we did in the previous sessions, wherein we will try to recall what all has been covered so far in this topic. Thereafter, we will talk about the skeletal vibrations, what are they, where do they come from, what do they signify and things like that. Thereafter, we will move on to characteristic group frequencies or functional group frequencies or group frequencies as they are typically called, and see their significance. Then we will try to see what are the factors which affect group frequencies, and the factors we will be taking up would be resonance, hydrogen bonding and the physical state of the system we are talking about. Then we will briefly touch upon the intensities of spectral lines, that means which spectral lines are going to be intense, which are not going to be intense, and so on and so forth. And towards the end, we will try to sum up what we do today. So, with that kind of a brief introduction to how we are going to proceed, let us make a beginning by recalling what we have done earlier so far. If you recall that we started our discussion of vibrational spectroscopy by seeing that how do we model a molecular vibration. We started by modeling them in terms of a harmonic oscillator, and thereafter we realized that this was not an adequate representation. We moved on to an harmonic oscillator. So, there are two things we did talk about, and in this process when we modeled the molecular vibrations in terms of harmonic oscillator and an harmonic oscillator, we kind of made some kind of a quantum mechanical approach to that, and then saw the results what we get by assuming the molecule to be vibrating as a harmonic oscillator or as an anharmonic oscillator, and compare the two kind of results there. Then thereafter we moved on to formulating some kind of an expression for calculating the vibrational mode of polyatomic molecules, because what happens is we started our discussion with purely diatomic molecule. It was simple. Thereafter, when we moved on to a polyatomic molecule, we realized that a polyatomic molecule can have wide variety of vibrational modes. So, we formulated an expression that what are different possible number of vibrational modes are there, and then thereafter we saw that how do we calculate them for a given kind of molecule. We took some examples, and then we formulated using the formulation we calculated the number of vibrational mode for molecules, say like carbon dioxide or water and things like that. Then also we ascertained whether a given vibrational mode is going to be IR active or not, because you will remember that the prerequisite for a mode of vibration to be IR active is that there must be accompanied by some kind of a change in the dipole moment. Thereafter, we explained the origin of additional vibrational bands for polyatomic molecules. These are the bands which occur in addition to the fundamental and overtones and things like that. Let us recall that for a molecule, a linear molecule having n atoms, there would be 3 n minus 5 vibration degrees of freedom, whereas for a non-linear molecule, they will be having 3 n minus 6 vibration degrees of freedom. And suppose I am looking for a molecule containing n atoms, the spectrum will be very complicated one, because that will have signals arising out of the fundamentals, the fundamental vibrations which we just numbered here 3 n minus 5 or 3 n minus 6. Then also there will be the corresponding overtones, because for any fundamental vibration there will be first overtone, there will be second overtone, and so on and so forth. All that we have discussed earlier. So, essentially what I want to bring home is that the vibration spectrum of a simple molecule, a polyatomic molecule, will be quite complicated one. This complication is augmented by additional bands, they are called as combination bands. What happens is there could be bands which are arising as a combination of sum of two interacting bands. That means the frequency will be sum of the two vibration frequencies there. There could be two fundamentals. Similarly, you also have difference bands. That means the frequency of such a difference band will be difference of the two vibration frequencies. Further, we also have provision or the possibilities of some kind of a Fermi resonance. In case of Fermi resonance, you will recall what happens is that one of the fundamental vibration mode interacts with overtone of another vibration, and that leads to generation of new signals there. That is called as Fermi resonance. Now, so all these put together make the vibration spectrum quite complicated one. We can say that the IR spectrum consists of a large number of signals that we have seen in the previous sessions also. So, that is the kind of thing we have covered so far. Now, how do we go about from here? How do we go about this? We try to see that all these signals what we get there, these signals can be put in, because basically what we want to do is we want to make use of the IR spectrum in terms of structural determination of molecules. To effect that, what we do is we group over all these frequencies into two broad groups. They are referred to as skeletal vibrations, and also the second group is your characteristic group frequencies. We will understand each one of them one by one. Let us begin with skeletal vibrations. Now, skeletal vibrations basically they arise from the coupling of vibrations over a large part of or over the complete molecule. What it means is that we have a molecule. In a molecule, there are different vibration modes are there. So, a number of vibration modes which are spread over the whole molecule, they all couple and they give rise to a vibration mode which is called as a skeletal vibration. In case of a skeletal vibration, these vibrations involve some kind of a displacement of either all or nearly all the atoms in the molecule, because that is why they are called as skeleton, and these are typically observed in the range of about 1500 to 650 centimeter inverse. Now, this is very significant here. The significant is that firstly that these vibrations which we are observing in the this region, they are quite sensitive to the steric or electronic effects in the molecule. Suppose there is a small change, there will be small structural change or electronic change in the molecule that will lead to a large change in the spectral vibration what we observe. Now, as a consequence of these, the spectrum of a molecule may have a very large number of absorption bands present over there, and these vibrations actually happen to be very unique to a molecule, and they have a very typical pattern, or as it is called as a fingerprint of the molecule as a whole. And this region which I mentioned from 1500 to 650 centimeter inverse is called as the fingerprint region. It is like the fingerprints we talk about in case of human beings, because as we know that the fingerprints of two different human beings do not match. Same is true of the molecules also, because this region is very pertinent in that sense of it. It has a very important kind of application in terms of determination of structure of molecules. We touch upon that a little later. Now, but though there are a large number of bands in this region, but you do not need to assign each one of them. What we do is we make use of the region as a whole. How do we do that? Let us see. One of the ways of using this fingerprint region is that if I have got two molecules, say there is a molecule A, suppose I have a natural sample of some compound A. I take the IR spectrum that looks something which is shown over here, it is a representative sample there. And suppose I make the same molecule in the laboratory, I want to see whether I have got the same molecule or not. What do? I run the two spectra simultaneously. That means I run one spectrum first of the natural molecule, then run the spectra of the synthetic molecule, and then see whether the fingerprint region match or not. This is a region I have to focus my attention on. So, this example given here, we find that the two spectra A and B in this region match exactly. So, we can say the molecule which we have created synthetically is identical to natural molecule over there. So, that means I am able to establish the authenticity of the compound. That is one very significant application of fingerprint region. Going further, another very important observation here, that means you may have very closely related molecules, but they will have very different fingerprints. Like in human beings, suppose there are two identical twins, even identical twins do not have the same fingerprints. Same holds true here. So, I am having two very similar molecules, propanol 1 and propanol 2. We find that this fingerprint region, the two are very different. Say for propanol, the blue spectrum here is for propanol 1 and the red one is for propanol 2. We find the two are quite different there. Let us take the expanded view of the two. Do you see that in this region we find that the fingerprints of the two molecules are very different. That is a very important tool in the hand of spectroscopist to make use of this region to establish the authenticity or otherwise of a given molecule. Let us move on to the second group of frequencies, which are called as characteristic group frequencies. These are also referred to as just group frequencies or functional group frequencies, and so on and so forth. There are a variety of ways of saying the same thing. Now, what is important is contrast this with a skeleton vibration. Skeleton vibrations were kind of the whole molecule was involved in that, whereas in case of group frequencies we have a small part of the molecule which is involved in that. So, the two are very different there. These usually are assigned to a particular part of a molecule and are independent of the structure of the molecule as a whole. Let us try to contrast here. contrast between the skeleton vibration and group frequencies. Skeleton vibrations were pertaining to the whole molecule. Suppose there is a molecule there, the whole molecule is involved in that kind of a vibration. Whereas when I am talking about a group frequency or characteristic group, what happens is you have the bulk of the molecule, maybe there is a small functional group. So this has a different, some sort of frequencies there. Now suppose I change this bulk, but my functional group remains the same, it will have similar kind of a frequency there. That is what we mean by group frequencies. That means these frequencies pertain to a group of atoms in a molecule. A small part of the molecule is involved in that, not the molecule as a whole. We will clarify as we move further. Now typically in a spectrum, these are observed in regions above and below that of the skeleton vibrations. Skeleton vibrations were from 1500 to 650 centimeter inverse, whereas this will be lower than that and above that. So that is the two have got very kind of a complementary region in which they are appearing there. So skeleton vibrations appear in the fingerprint region and group frequencies appear outside that. Now as against the skeleton vibration, the characteristic group frequencies, they involve displacement of a very small portion of the molecule, which is independent of rest of the molecule. And if the force constant of the bond is independent of the molecular moiety, the group frequency is independent of the rest of the molecule. Let me take an example and explain it to you. If you look at the CH stretching vibration for a terminal alkyne group, it is typically observed around 3300 centimeter inverse. Let us take the example of 1 octane. If you look at the spectrum, what you find is that this is your triple bond CH. This CH I am referring to. This CH vibration is observed around 3313 centimeter inverse. So around 3300 centimeter inverse. That is typical of a terminal CH stretching of an alkyne group. Now why so? Why is it that we are observing it here? Let us try to rationalize that. How do we rationalize that is, we can visualize this molecule of octane. Octane you know is C8H14. We can visualize that molecule as follows. This is the bulk of the molecule is C8H13, that all the part of the carbon chain and all the respective hydrogens on that. And this is my CH bond over there. That is the point I am trying to focus attention to. Now as you know that the vibration frequency of a vibration molecule is given by 1 by 2 pi k by mu hertz, and where mu happens to be the reduced mass, and you know that what is the reduced mass over there. Now in this molecule, the reduced mass will be given by the mass of hydrogen atom and mass of CH. Mu, that is the reduced mass of this molecule, will be mH m C8H13 divided by mH plus m C8H13. So that means this is the bulk of the molecule, this is my hydrogen atom there. Now for such a system, what we can do is we can make an assumption there. We make an assumption that the mass of C8H13 is approximately equal to mH plus m C8H13. That means this denominator I am assuming, that means basically I am trying to ignore the mass of hydrogen as compared to that of the bulk of the molecule. When I do that, so this gets ignored there, then what happens is this term gets cancelled with this term over there, and my reduced mass comes out to be just the mass of hydrogen atom. That means for this molecule, under this assuming situation, the vibration frequency will now come out to be 1 by 2 pi square root of k by mH. Now my vibration frequency of this particular functional group or this particular bond here will depend only on the mass of this atom and will be independent of this bulk of the molecule. That is when we say that it is independent of the molecule there. That means only this group is of interest to me. So in such a situation, if you try to compute, it will come out to be what is experimentally observed. Now instead of, if it happens to be C8H13 or maybe if it happens to be C9H15 or so on and so forth, if this bulk increases, still this will remain the same. This assumption will be true and my observation will be holding true there. But there is a small word of caution here, that is, this kind of an approximation does not hold good for small or lighter molecules, because in that case this validation will not be there. That means the assumption which we make here, that we can ignore the mass of hydrogen atom as compared to the bulk of the molecule there, may not hold true if the molecule happens to be a simple molecule there. So that is the way we rationalize the so called constancy of group frequencies of the molecules as observed in the IR spectrum there. Now let us take some examples there. Typically alcohols will have the group frequencies in the range of about 3200 to 3600 centimeter inverse. Now if you look at a CH, that means I am talking about the vibration frequency of carbon hydrogen bond. In case of alkanes, that's the kind of range we have, about 2850 to 2960. That of alkenes, it becomes slightly more, that is 3020 to 3080. That of alkynes is, I just mentioned, about 3300 centimeter inverse. Similarly, if I look at the group frequencies for say carbon-carbon stretching in case of alkanes, alkenes, alkynes, so that is the kind of pattern we have. Alkanes will be 1200, 1650 and so on and so forth. Carbonyl group or ketones typically will have vibration frequencies of the order of about 1700 centimeter inverse. There are many more. If you look into any book on IR spectrum or any spectroscopic book, it will give you a large number of tables wherein all these have been compiled together, because they are quite useful in terms of interpreting IR spectrum, because IR spectrum we want to use it to find out the structure of a molecule. So, these tables become very handy over there. That kind of interpretation of spectrum probably you will be taking up in a different course where we talk about the applications of spectroscopy. In this course, which is purely based on the conceptual part or the physical chemistry part of it, we are talking about the concept of it. The applications we will be taking up in a course of organic chemistry, which will be done separately there. Okay. Now, these group frequencies, they follow very logical trends, and you have to remember here that is that equation I just mentioned, the vibration frequency, that frequency that nu is equal to 1 by 2 pi k by mu is a very important formula for us, which is very handy there. Let us see how does it help us. Now, if you look at, suppose I am trying to compare the vibration frequencies, some bonds there, say CH, CD, CC. So, in all these three, what we do is we are keeping one of the atoms constant, say carbon, and the second atom I am changing from hydrogen to deuterium to carbon there. Now, I am increasing the mass of the atom there. So, what happens as a consequence of that? What will happen is, atom happens to be heavier, the reduced mass will change, reduced mass will become large. As a consequence, it will become large because reduced mass is m1 into m2 by m1 plus m2. So, if m2 increases, reduced mass increases, and since reduced mass happens to be in the denominator in this formula, what will happen? The vibration frequency will decrease, and that is what we are observing here. Say for CH, it is about 3000 centimeter inverse, CD it happens to 2100, CC it comes out to be 1200. So, there is a clear cut observation of this particular formula is there. Now, but we have to see here that in this formula we are just trying to interpret or trying to argue out on the basis of just one parameter, that is the reduced mass. Even the K also matters there, because these three bonds I am talking about, CH, CD, CC, will have different values of K also. That means bond strength also is going to matter. There will be determinant in the determination of this vibration frequency there, but we are ignoring for the argument's sake there. That means we are assuming that they happen to have the same bond strength, which they do not have it. But all said and done, the order, the pattern remains what is expected from the formula over here. That is one observation. Going further, what we see is that stronger the bond between a pair of atoms, higher is the vibration frequency. Let us take some examples here. Say look at CC bond, CC single bond, CC double bond, CC triple bond. In this case, what we have done is both the atom in the three systems here, they remain the same. As a consequence, what happens is our reduced mass becomes constant. So, that means in this case, the factor which is going to determine the vibration frequency will be just the K, that is the force constant there, or the bond strength, so to say. And if you look at the bond strengths here, the bond energies, which is about 83, 146 and 200 kilocalories per mole for these three bonds here. As a consequence, what we see is that as K is increasing, so is the vibration frequency there. So, there is a one-to-one correlation. Similarly, we can see for CN single bond, CN double bond, CN triple bond, we find that the bond strength is increasing, so is the vibration frequency. So, they are very straightforward, because this formula I just mentioned is very important for us. Now, let us move a little further and see what are the factors which affect these kind of group frequencies. And the factors happen to be, I was just talking about the three of such factors. One is resonance, the second one is hydrogen bonding, and the third one is the physical state. Let us take these one by one. First, resonance. Suppose there are certain groups having comparable vibration frequencies in isolation. Suppose I have got a carbonyl group, say about 1700 centimeter inverse. That is a kind of vibration frequency, typical value for that. Or you have an alkene say around 1650 centimeter inverse or so. So, when the two of such groups which have vibrational frequencies in the neighborhood, they are present in a molecule together. Say, I will take the example here. What I am saying is, if I look at a ketone, a carbonyl group, it has a typical value of 1700 or 1710 centimeter inverse. But if I have a carbonyl group which is in the neighborhood of an alkene, which also has a vibrational frequency around 1615 or 16, around that range. So, what happens is they undergo resonance there. That means what happens is you can have the movement of electrons as shown over there. As a consequence, what happens, if you look at this here, you had C double bond O. It was a double bond with this kind of vibrational frequency. Now, because of this resonance here, what has happened is that this has acquired the so called double bond character of this bond, CO bond has become lesser, and same is true of even that CC bond also. This is no more a double bond, the double bond character has reduced. As a consequence, what happens is, since the double bond character reduces, that means the force constant or the bond strength decreases. As a consequence, the vibrational frequency also decreases, because in this case the reduced mass is not getting altered by the resonance there. Because of resonance, it is the force constant or the bond strength which is getting reduced, and thereby the vibrational frequency also comes down there. So, there are three more examples here. So, you can see a carbonyl group here in conjugation with an alkene here, another example, yet another one. You find that each one of them has got roughly similar kind of a vibrational frequency, which is different from what we had in case of an isolated carbonyl group. These all are carbonyl group frequencies there. So, you find that from about 1710 it has come down to 1687, 1690 or 1685. So, that is the kind of observation we have. So, I would like you to mark one simple thing here, that is, if anything which happens to the molecule and as a consequence of that, suppose some bond becomes stronger, the vibration frequency will increase. If the bond becomes weakened, the vibration frequency will come down. So, that is a golden rule, so to say, because in a molecule, if some effect is there, we are not changing any part of the molecule. So, any external effect, the molecular structure remains the same. So, in the formula that nu to be equal to 1 by 2 pi k by mu, it is a k which is going to determine the vibration frequency there. So, anything which changes k, it increases k, vibration frequency will increase. If it decreases k, the vibration frequency will come down. You can see here also, because if you look at the vibration frequency of this particular part of the molecule, this is CC single bond. Because of this resonance there, it has acquired some kind of double bond character. So, the vibration frequency pertaining to this particular bond, I am just putting it just for sake of it, that will be now increased there, because the bond strength has become more. I am sure that this golden rule you keep in mind. Let us move further a little. Let us take the second factor which affects the group frequencies, and that happens to be hydrogen bonding. And I am sure that you all know that hydrogen bonding is observed in systems containing a proton donor, that means some kind of an XH, something which can give a hydrogen atom, and a proton acceptor. They are not giving out, it is just a part of a molecule, a group in a molecule which can provide a hydrogen atom for hydrogen bonding. And in a second molecule or in the same molecule, you can have a part of the molecule, an acceptor, in this case I am depicting as Y, that can bind to this hydrogen atom. Let me take some examples here. Now, this X and Y are electronegative in nature, and Y also possesses a lone pair of electrons. Let me take some examples here. Common donors are, say, a carboxyl group, an hydroxyl group, NH2, CONH2. So, all of them have got hydrogen that can lend itself for hydrogen bonding. And on the other hand, the common acceptors are typically oxygen, say a carbonyl group. And the carbonyl group oxygen atom has got lone pairs on that. So, that can accept a proton to bind with that. It's not, there is no transfer of proton there, it is just that the proton can interact with it. Or some kind of nitrogen atom could be there, or halogens are there. So, they are the ones which are the contributor of a hydrogen bond formation between the molecules or within the molecule. Now, let me take what happens as a consequence of hydrogen bonding. What happens as a consequence is that because of hydrogen bonding, the force constants of the bonds, that means the donor and the acceptor, they get altered, and as a consequence the vibration frequency also changes. Let me take an example. Suppose you got this is a carboxylic acid. This is a very standard typical example to quote here. that is called as a dimerization of a carboxylic acid. So, what we see is in this case of a dimerization, let us see what is happening here. What is happening is, say from this molecule here RCOOH here, this oxygen atom is acting as an acceptor there, and from this molecule here, this OH is acting as a donor there. This hydrogen atom is contributing to the hydrogen bond. This is a kind of hydrogen bond I am sure that you all are familiar with. Same is true over here also. So, this is an acceptor here, this is a donor there. Now, when this hydrogen bonding takes place, what happens is, because now oxygen has certain binding capability, it is bound to this carbon atom to begin with, but now because of this additional interaction with hydrogen atom, this carbonyl group here, this bond gets slightly weakened. Since it gets slightly weakened, the force constant reduces. As a consequence, the vibrational frequency also decreases. And similarly, this also, because this bond also will get slightly elongated, because when the hydrogen atom interacts with this bond gets elongated. As a consequence, that force constant decreases, and as a consequence what happens is, because of this hydrogen bonding, the vibration frequencies of the bonds with the donor as well as the acceptor atoms decreases. So, that is a typical observation we have vis-a-vis the consequence of hydrogen bonding on the group frequencies of the molecules. Okay. Let us move on to a third very simple parameter, the physical state. What is observed is that a change in the physical state also is found to cause shift in the vibrational frequency, and the typical trends we have, a polar molecule, the order happens to be something like this. That means, the vibration frequency in the gaseous phase happens to be more than in the liquid, or in solution they will be similar, and which will be greater than that of the solid state there, or solid phase there. But for non-polar molecules, what is observed is that there is no significant shift in the frequency of symmetrical stretching vibrations. That means, if I talk about symmetrical stretching vibration for a non-polar molecule, and if I change the phase of physical state, there is not much of a significant effect. But if I talk about the other kind of vibrations, say the bending vibration or otherwise, so there will be some changes, but not as significant as that for the polar molecules. That is a general kind of an observation we have about the physical state affecting the group frequencies there. Okay. Let us move on to intensity of signals. Let us see, because we know that if you look at an IR spectrum, we find that certain signals are weak, certain are very, very weak, certain are very, very intense or strong signals are there. What determines that? The intensity of signal, we know that the answer to that question basically lies in the prerequisite to observe a vibrational spectrum. You remember that that for any molecule to show an IR activity, we find that in the course of a vibration, the dipole moment of the molecule must change. That is a kind of a prerequisite we have. If any molecular vibration is not accompanied by a change dipole moment, that will not be observed in IR spectrum. Now, similarly, what happens is, now if a bond happens to be highly polar, if the polarity of bond is more, what will happen is, if that bond vibrates, the change in dipole moment will be more. As a consequence, the signal will be intense. So, that is a kind of a thumb rule we have. That means, if intense signals are there, probably you can ascribe them to be arising out of parts of the molecule which are polar in nature. So, let us take the example here. We see that the signal of a carbonyl group will be larger than that of a C double bond N, which in turn will be larger than that of the C double bond C, and so on and so forth. Or we can take some more examples here, say that of an OH group, the typical signals are very, very intense there, NH will be slightly lesser in intensity, and CH will be still lesser. So, that is the kind of trends we have with us. Now, let us sum up what we have done today. What we have done today is that we reviewed the contents of previous sessions, that is what we began with. Thereafter, we emphasized that the IR spectrum of a molecule consists of a large number of signals, and that large number of signals probably can be put into two broad groups there, and they happen to be the skeleton vibrations and the group frequencies there. Thereafter, we explained that the skeleton vibrations, they involve the movement of nearly roughly most of the atoms of the molecule as a whole, so to say, and they happen to be very unique and constitute what is called as a fingerprint region of the spectrum, because they have got every molecule has got its own fingerprint in the IR spectrum there. Thereafter, we explained the concept of group frequencies, wherein we mentioned that certain part of the molecule, the frequencies of that are very characteristic of it. They are independent of the bulk of the molecule there. Having done that, we discussed the certain factors which affect the functional group frequencies. We took up 3 factors: resonance, hydrogen bonding, or the physical state. And thereafter, we briefly touched upon the variation in signal intensity on the basis of nature of the molecule. Say the polar molecule signals will be more intense that of the as against that of the non-polar molecules, and so on and so forth. So with this, we complete our discussion on vibrational spectroscopy, and now in the future sections we will talk about say electronic spectroscopy. Till then, thank you very much.